Hello everyone. I'm going to talk about a new interpretation of quantum mechanics, which I call it the global approximation interpretation, or standard interpretation. First of all, why the name? The word global comes from the fact that everything talked about in quantum mechanics is a wave, or de Broglie matter wave, and the waves are global. Also, Schrödinger equation is a global differential equation. To solve it, we have to know all information of the whole space, or the global condition of the system. So, all quantum states, or quanta, must be global. And the word approximation comes from the formulation and its interpretation of current quantum mechanics, that is, Schrödinger equation and the wave function. All fundamental interactions are local and relativistic, so the global non-relativistic formulation must be an approximation. The word standard comes from the standard model, which deals with the fundamental particle and the interactions. Quantum mechanics is supposed to deal with the microscopic world, and the standard model provides a picture of the microscopic world. As our interpretation based on standard model, so we can call it the standard interpretation. What is standard interpretation trying to achieve? Quantum mechanics have been around for more than 100 years, but we are still frustrated in understanding it. Richard Feynman insulted the whole physics community up to this day. Even Einstein used the word spooky to describe a physical phenomenon that no one has any idea. GAI, or standard interpretation, tries to help everyone understand quantum mechanics intuitively. And we can tell Einstein that there's nothing spooky. Everything is just as plain as he always believed. Now a little about myself. About 35 years ago, when I first saw Schrödinger equation in a general physics class, I was mesmerized, staring at the equation for a long time. The more I tried to learn about quantum mechanics, the more I was confused. So I walked a long way to officially study quantum mechanics in Peking University, or Beijing University, mentored by Professor Zeng Jingyan, which is the best quantum mechanics scientist and teacher in China at the time. Pursuing the understanding of quantum mechanics is not an ideal career option, so I also worked in other fields such as computational physics, high-performance computing, plasma physics and nuclear fusion, etc. But I never stopped thinking about the fundamental concepts of quantum mechanics. I thought I got something about the quantum mechanics 10 years ago. And start talking and made enemies. Last year, I believed I have connected all the dots and wrote a paper. You can find the link of the paper below. Let's talk about the key differences between standard interpretation and the traditional Copenhagen interpretation. The first is the timing. When Copenhagen interpretation was proposed about 100 years ago, we knew very little about the fundamental interactions and particles. Of course, we knew much better now. we're on a much better ground of understanding the microscopic world at the fundamental level. About the basis of the theory, Copenhagen interpretation needs many assumptions, such as quantization, meta-wave, even Schrödinger equation, because Schrödinger couldn't explain how he got it, but it works. In Copenhagen interpretation, quantization of energy and angular momentum is a basic assumption. But in standard interpretation, it is the natural emergence. Schrödinger equation is usually considered as the wave equation of any quantum, but in form, it is a diffusion equation. In Copenhagen interpretation, wave function is the probability distribution, but in standard interpretation, it is energy density. In Copenhagen interpretation, measurement is basically the probabilistic sampling, which is not a physical process, and is discontinuous. In standard interpretation, measurement is certain interaction output. Quantum entanglement is not discussed in Copenhagen interpretation, but comes from the implied quantum non-locality or globality. In standard interpretation, like all other quantum phenomena, quantum entanglement has a global nature. In standard interpretation, all quantum states are established and require some time, like all classical global modes. This concept is not in the scope of Copenhagen interpretation. Ideal coherence is implied in the derivation of Schrödinger equation. So in Copenhagen interpretation, all quanta or everything are ideally coherent. In standard interpretation, because all quanta are established, the degree of coherence depends on the condition of the interaction or global situation. About the relation with the classical mechanics or classical physics, Copenhagen interpretation usually thinks quantum mechanics and classical mechanics are inherently different. But in standard interpretation, there's no such difference at all. Both are extremes of ideal approximation in the opposite direction. In Copenhagen interpretation, definition of a particle is not very clear. Usually people think a particle is a point with wave-particle duality, together with some intrinsic properties, such as spin and the rest mass. Standard interpretation uses standard model picture of a particle, or the disturbance mode of energy to space-time, usually some stable modes. In Copenhagen interpretation, the concept of a photon is not discussed in the first quantization, and it behaves like other identical particles in the second quantization theories, also with wave-particle duality. In standard interpretation, it is also a disturbance mode to space-time, like other particles, but unstable or always traveling, because it has no rest mass. In Copenhagen interpretation, reality is meaningless before measurement. Standard interpretation takes reality differently. In standard interpretation, reality is relative because measurement bases on interaction, and it will change the project. Considering Bohr's instrumentalism. In Copenhagen interpretation, the world is indeterministic, while in standard interpretation, because of the relative reality, the world is relatively determined. The above differences are mostly self-explaining. I guess someone already gets everything about standard interpretation. The question is there a proof? Well, this is actually an extremely unfair request to standard interpretation because all previous interpretations are more or less conceptual or philosophical, such as Schrödinger's cat paradox. Schrödinger thinks one way, but Copenhagen interpretation thinks the other way. The debate is philosophical because Copenhagen interpretation basically forbidden experimental proof. However, we can verify standard interpretation step by step in detail to show how quantum states are established, such as in quantum entanglement experiment, while Copenhagen interpretation definitely has no idea. We can also find proof in other experiments such as quantum eraser diagnosis, and electron magnetism. Now let's talk about the puzzles quantum mechanics raises. Before quantum mechanics, scientists were quite satisfied because they thought they had already well understood the whole physical world, with only two exceptions. After the establishment of quantum mechanics, we have a theory which can do the calculation right, but incomprehensible. People say, no one understands quantum mechanics, or shut up and do the calculation. There are not just one, but many puzzles imposed by quantum mechanics, such as wave-particle duality. Nothing can be both a classic wave and a classical particle. Even people talk all the time. We heard people saying, okay, I know what you are talking about, but why? If you thought about quantum mechanics before, you should know these puzzling concepts as listed here. Like, what is measurement? How do a wave function collapse? And instantaneously? How about the discontinuous physical quantities? I know what uncertainty principle is, but why? And what is a photon? What is a spin? Low reality? Quantum entanglement? Non-locality? What happened to the principle of locality? Delayed choice interference experiments? And everything just happens randomly? Okay, now let's talk about the standard model and what it told us about the fundamental particles and interactions. This is not a talk about standard model, so I will be brief here. and please check on the professional talks. What I'm trying to do here is to tell that now that we have the knowledge, and we shouldn't, why shouldn't we take advantage of it? The basic conclusions from standard model are: the interactions are extremely complex, trivial, but the theory is rigorously tested. Interactions are very sophisticated, as well as the calculations. The standard model is based on quantum field theory, and it is incorporated with special theory of relativity. So all interactions are local or comply to the principle of locality. Basic physical quantities are continuous. All the derivational formulation in the Lagrangian is groundless. There are three keywords here: complex, local, and continuous. Every particle is an extremely complex existence from the perspective of Feynman rules. In laboratory quantum experiments, only electromagnetic interaction is involved, and every space-time point is equal. And the differences come from the energy density. Or maybe how energy distributed in which degrees of freedom. In the case of electromagnetic interaction, only energy density matters. Now about Schrödinger equation. We don't know how Schrödinger got the equation, but there's a popular derivation of Schrödinger equation in the textbooks. In the derivation of Schrödinger equation, matter wave is defined as an ideal plane wave, which is also the form of the electromagnetic wave, or light. In form, Schrödinger equation is a diffusion equation with an imaginary diffusion coefficient. If we drop potential part, or in free space, and move the coefficients to the right, Schrödinger equation is a diffusion equation of waves. Imaginary coefficient means attenuation or wave behavior. It may imply waves remained after sufficient diffusion. Of course, this is a guessing, not a proof. But still, the solution to Schrödinger equation is a global distribution of something. We can call it quantum or particle, under the restriction of boundary conditions in the given potential. We should be aware that the solution of wave function is global. There is no interaction, only a global potential. Potential means the restriction or interaction between the particle or quantum and the potential, or global condition. And the interaction is instant. which requires no time. For electromagnetic interaction, this implies infinite speed of light. It is interesting to ask why the matter wave assumption or ideal plane wave assumption works well in the derivation of Schrödinger equation. In the case of electromagnetic interaction, Schrödinger equation implies infinite speed of action propagation. But in reality, interactions are local and with finite propagation velocity. Generally, for local interaction to achieve a stable global vibration state, only certain modes exist, that is, eigenmodes or eigenstates. It also takes some time to establish the stable global eigenmode. And the solution to the equation is the final state. This is similar to classical wave behavior, such as in music instruments. The musical notes are the eigenmodes, and it would take a short time to fully establish. In atomic scale, speed of light is tremendous, and the size is small. Eigenstates can be achieved almost instantaneously. So we can say Schrödinger equation gives the non-relativistic limit of a wave system, and is ideal. Once we have the Schrödinger equation, we can solve it in various situations and get different set of eigenstates. These eigenstates are discontinuous in basic physical quantities, such as energy and angular momentum. Before Schrödinger equation came around, quantization is an assumption or assumed principle. Planck, Einstein, Bohr, and Rutherford all proposed their own version of quantization principle. With Schrödinger equation and the boundary conditions, quantization becomes a natural occurrence or emergence. We no longer need Planck's energy quantization assumption. In the case of blackbody radiation, the blackbody has to be made of something, which is eventually atoms, with discrete energy levels, and automatically meet Planck's assumption of quantized energy, absorption, and emittance. What are particles? When we talk about the particle, we usually mean classical picture of particle, which is a point, even in quantum mechanics. However, this is certainly not true, but mostly close. The only exception is a photon. The official definition of a particle in quantum field theory is still different from standard interpretation. In standard interpretation, a particle is a disturbance mode of energy to space-time, usually stable, like a standing wave or a whirl. An elementary particle in quantum field theory might be a part of some composite mode, such as a baryon or a gluon. Photon is an exception. We will talk about it later. We have the concept of elementary particles, but no quantum. We cannot make a quantum. By definition, a quantum should be anything described by Schrödinger equation. It should be an ideal wave. In reality, it can be anything, from an elementary particle to macroscopic objects. Everything is a non-ideal quantum, but nothing is an ideal one. In Copenhagen interpretation, a quantum is its wave function, which is a global solution to Schrödinger equation, and an ideal wave. It is also the sum of all possibilities. In standard interpretation, the definition of quantum is the same, but it is a global approximation, and its value describes its energy density. In reality, a quantum is established. If it is well established, then it is close to an ideal quantum. Otherwise, we have bad coherence and more classical features. In standard interpretation, we believe that the public concept of quantum entanglement is a misnet, and the Bell experiments have been misinterpreted. Like all other quantum states, quantum entanglement state is an established global state. It is globality, not non-locality. We can prove it experimentally. Quantum entanglement deserves an entire separate talk, but we propose experiments to test the claim of standard interpretation, such as check non-pair correlation using incoherent light excitation, and separate pair creation and detection in time. I have another video talking about quantum entanglement in this channel. Quantum entanglement only happens in pairs, actually multiple parties. Let's concentrate on pairs. So if non-pair photons or asynchronous detection are also correlated, then it is a wave property. The second experimental proposal is because wave behavior needs coherence, we can use incoherent light source with the right color other than laser to create photon pairs to see if the correlation is still there. And the third experiment is entanglement interpretation assumes a three-step time sequence. We can ensure the time sequence by fast shuttles to separate photon pair creation and detection to see if the correlation still exists. Some major arguments of the globality of quantum entanglement are the public concept of instantaneous remote influence is a causal description, but Bell experiments only proved correlation, not causality. Causality description violates the principle of locality proposed by special theory of relativity. There is no interaction between the remote, separate particles, and any causal interaction can surely be used to transmit information, but quantum entanglement cannot. If the spooky quantum entanglement concept is correct, then the whole universe could be entangled. Such a world is irreducible and cannot be understood. Also, the popular metaphors of quantum entanglement are fatally flawed. In standard interpretation, quantum non-locality is a misunderstood global feature of quantum states. There is no interaction, so it is not spooky at all. The entanglement has to be established, such as resonance as in particle entanglement, or global mode as in photon entanglement. Quantum non-locality is a common feature of all global quantum or wave states. It's not special at all. Amazingly, after a few hundred years of fierce debate, we thought we finally found out what light is, or what photon is, and award a Nobel Prize to Einstein for his contribution in the understanding of light. But Einstein himself is very confused about the concept of photon all his life. I cannot cover all topics of light in detail in this talk, but will list some arguments which are absent in textbooks. Of course, photon travels at the speed of light, but every photon, like all other particles, involves global spacetime contribution. Whether it is quantized with a finite spin is the confusing part, because atomic forbidden transitions does happen, which means the angular momentum of the photon is not 1. It can be 2, 3, or even higher. We also have a concept of photon orbital angular momentum, but its physical picture is the same as the spin. The picture of a photon emission is not so clear. Photon emission lines mostly happen in a resonating environment. We cannot answer questions like, how long does it take to emit a photon? Or is it just a wave? None of the previous interpretations of quantum mechanics explains photon, or just describe it as a wave-particle duality. But in standard interpretation, we derived from standard model that low energy photon is just electromagnetic wave involving every spacetime point, and high energy photon or gamma ray more like are the localized particles due to different energy density. The link between electromagnetic radiation and gamma ray might be the headlight effect from the special theory of relativity. Whether the spin of the photon is quantized or not depends on the radiation source or the global condition, such as resonance, between which atomic energy levels For gamma ray, the spin is 1, and it behaves just like a localized particle. The question of reality kind of originated from Copenhagen interpretation of quantum mechanics. Physicists were quite confident about the objectiveness of the reality in Newtonian time. Copenhagen interpretation confused people by bringing out questions like, does the moon exist if I can't see it? Is a cat live or dead before observation? Einstein, Schrödinger have different opinions against Bohr and Heisenberg. Except for the millennium debate on realism and idealism, now we have one more question. Is there a reality before measurement? Copenhagen interpretation thinks that it is meaningless to talk about an unmeasured state. For a standalone electron, does it have a specific spin? Copenhagen interpretation think this is a meaningless question and formulated the superposition of up and down spin. Measurement randomly collapses it into a definite state of up or down. After measurement, it is well defined. Standard interpretation defines measurement as some kind of interaction. So the interaction will change the state of the electron. In the case of magnetic measurement, the spin could be created and it will show diamagnetism or just aligns to the magnetic field and be paramagnetic. Even if the experiment is too difficult to conduct, we can still argue that there is a reality, because our calculation of electron fits the experiment perfectly. All the details we use in the calculation is the reality of the electron. So, standard interpretation believes there is a reality before measurement. In Schrödinger's cat debate, Schrödinger can tell Bohr, if I close my eye, can I say, now you can be any superposition state other than yourself? Is that right, Professor Bohr? Or is the superposition of a dead and alive cat a reality? In standard interpretation, measurement is based on interaction. Depending on the robustness of the object, information extracted from the interaction is relatively reliable. Or measurement-based reality is relative. The relativity of reality can manifest it as credibility or precision, as in everyday life. Copenhagen interpretation is indeterministic because of its probability interpretation. Standard interpretation is deterministic because it acknowledges reality. However, this is different from Newtonian determinism. Newtonian determinism thinks the future of the world can be predicted by calculation. Standard interpretation determinism is an agnostic one, or relatively predictable one, because the reality is relative and long-term calculation is a long-term calculation of a complex system are impossible. Even in the Newtonian world, the calculation problem is the same. A partly predictable world conforms with our common sense. In Copenhagen interpretation, the physical meaning of quantum wave function is the probability of a particle appearance. It is the origin of wave-particle duality. However, probability is just a fraction, a number. It is dimensionless, so it is not a physical quantity. So Copenhagen interpretation of quantum wave function is not a physical definition. Comparing with classical wave function forms, we found quantum wave function should express energy density. As energy is the source of any physical change, standard interpretation explains wave-particle duality behavior more intuitively, which requires no collapsing. Energy density interpretation is also consistent with Copenhagen interpretation, because Copenhagen interpretation thinks a particle owns all its energy, but distributed by probability, that is, its wave function. The even deep origin of energy density and the similarity with classical electromagnetic wave is that in that scale, the only fundamental interaction involved is electromagnetic interaction. When quantum concept came around about more than 100 years ago, scientists have to answer why quantum world works differently and how to reconcile with the classical and the quantum world. Planck and Bohr both proposed their own version of correspondence principle. Later on, the coherence theory was proposed to deal with the coherence problem. In standard interpretation, we don't have the problem, because ideal coherence and the Schrödinger equation is only an approximation. They are the ideal wave limit of the system. When the limit is less and less ideal, and the global condition turns unfavorable, the system turns back to classical local interacting one. The key parameter here is the coherence range, which is determined by the system size and other global conditions. Why we have to use probability interpretation in the classical quantum mechanics or Copenhagen interpretation? That is, causality, or the principle of locality, comes from special theory of relativity, is one of the basic logic for us to understand the world. In classical world, the source of any disturbance or change is the cause of the event. Quantum events depend on global condition. When we toss a coin, if we can follow all intermediate states, the result is determined. Otherwise, we can only describe using probability. Quantum mechanics omits the intermediate processes from the initial state to the final quantum state. So the causality is lost, and we have to use probability. In Copenhagen interpretation, quantum mechanics poses a complete series of philosophies, challenges our classical common sense, such as quantization, probability, indeterminism, absence of reality, etc. In standard interpretation, we emphasize the holism of Schrödinger equation and quantum mechanics, as well as its approximation nature. All philosophic conflicts are solved in the understanding of standard interpretation, including atomism and continuum, reductionism and holism, determinism and indeterminism, materialism and idealism. The relativity of reality solved the relativity and determinism problem. In conclusion, with standard interpretation, we have just one single word and one set of rules. We don't have to distinguish between the classical and quantum words. Our understanding or intuition, including common sense logic and causality, is restored. We don't have to puzzle about the microscopic word and weird logic. We also have a unified philosophy. However, standard interpretation is not in favor of quantum computing, and that's why I'm not popular among quantum information community. I didn't cover all topics of quantum mechanics, but we should be able to answer all questions, such as those listed here, such as what is a vacuum, and what do quantum fluctuations mean? Do they come from somewhere, or just intrinsic? Is there zero-point energy everywhere? With the principle of standard interpretation, for the smart minds, I think they can figure out themselves. We also have a hint. Mathematical formulation is global by default. So how can us be more physical? To ask for experimental proof of an interpretation of quantum mechanics is outrageous. However, standard interpretation can have experimental proofs. For quantum state establishment, we can conduct dedicated coherence entanglement experiments or diagnose quantum eraser. For reality and electron spin claims, we can test the magnetism of the standalone electrons. So that's all. Thank everyone.